Zhang from the University of Seattle, of Washington and Seattle, who is going to speak about classification of simplicial algebras.
Thank you very much, Miller. So, too fast. Well, thank you again. Thank you, Mike, for the organizing this wonderful conference invitation and for the thanks to the institute. I'm not sure if this is right, but also you said IMI, same, right?
It's not.
IMI.
It's slightly different.
Ah,
IMI is the institute, and this is the international center that's associated to the institute.
okay. So this is right.
This is right.
Okay.
Mhm.
Nice. All right. So today I will going to talk about the classification of the simplicial algebras, and I'm going to point you on that. Sorry. Oh, too fast. So I'm going to talk about only one theorem today, which is kind of the classification of simplicial algebras, simple simplicial algebras. But the paper was a joint project with my students. So Zhang, Garcia, and Eric. So we are working on it and almost finished. Oh, I don't know. It's moving too fast. Okay. So coming back to the this only theorem, I use V for a simple simplicial O-algebra. The main result is that V is isomorphic to one of the following, like 1, 2, 3. If we require V to be unital, then there's a subcase of 2. So this is the.
So you had the definition earlier of the simple simplicial algebra. What is simple simplicial algebra?
Good question. So I have a red here. So this is an item I'm going to explain first. So I will explain simple, what simple mean, what is operand, what is an O-algebra means, what is simplicial. Also, these two algebras, if we go back, I have these symbols. I will explain all the terms. Okay. If after I explain all the terms, then I finish my talk. That's my plan. Yeah. So thanks. And if we have more time, I'm going to discuss why this is called a classification result, and if we still have time, then I'm going to tell you one key idea in the proof, right? If we don't have time, then we're not going to worry about that. That's the plan. Okay. So the first item I'm going to explain is the word simple. It is quite easy to explain the simple. So here's the definition. So we're talking about algebra. So let's think about associative algebra. What does a simple algebra mean? Just means there's no proper ideal, right? Only ideal is 0 or the ring cell. And this definition of simple applies to all algebras in my talk. An algebra or simplicial algebra is called simple if there is no proper ideal. Okay, that's not simple. Or if you have any morphism from this B to W, then the morphism must be injected because there's no proper ideal. Okay, this definition applies to all algebras. B algebra, Jordan algebra, Poisson algebra, whatever the algebra you can think of, we use the same definition of the simple. All right. So, for example, matrix algebra over field, it is simple as associative algebra. Bar algebra as associative algebra is simple, right? Then, of course, maybe we require some condition on the field. And a simplicial algebra, I haven't explained the word simplicial yet, but a simplicial algebra can be think of like a graded algebra or an algebra with different levels. Then if A is a simple algebra, then we look at the simplicial algebra. At each level is A, this will be a simple simplicial algebra. This means that we don't have any non-trivial or proper simplicial ideals. Okay, so this definition applies to all the objects, any algebra object. If there's no proper ideal, we cross it. All right. Simple Lie algebras, finite dimensional ones, this is type A, this is type B, C, D. Jordan algebras, also the finite dimensional ones, there's some classification. So lots of examples of simple algebras. So remember, when I say algebra, I'm not talking about associative algebra only. Any algebra we're talking about. All right. So now let's go back. So I explained the word simple. Right? Okay?
Agree.
Oh, agree. So should we agree?
On the screen.
Yeah, please stop.
If the person is simple, this means that the person has no ideas. Oh.
Okay.
All right.
Maybe I should just stay away from this.
Okay, yeah, okay.
No, he's looking good.
Okay. So I kind of leave the one hypothesis O to be a connected opera outside of theorem. Solution for this is that first of all, the theorem applies a broader algebra in the sense that if we have a G equivalent O-algebra, this is still fine. If we have algebra with half action, proper coaction, also fine. However, if we only consider operate case, we cannot delete this connected. We have example that we consider operand is not connected, then this fails. Okay, we do have example this fails. So this holds for more general context, but we do have some hypotheses on the operand.
Sorry, but field-based field is not a great features.
I should say that K is a phase Mitchell field at this point. Yeah.
No assumption on the characteristic or code, any field.
Not for this this result. No. I'm not quite sure if we can replace K by like a commutative ring at this point. I don't know, but the field is enough for this result.
No, you can't replace it by a ring because ring has lots of ideals. So that will create lots of two-sided ideals. So you can't replace K by the ring and still define the same way. Simplicity, because ring will have lots of ideals.
Yes.
So yeah. But field is okay. I mean, you don't need identity to
Right.
field because they can work to lifetime and algebra and that's it.
Okay, thank you. All right, so what's next? I want to explain operand and O-algebra. Let's see. Operand. So first, let me give you some examples of operand. First one is called associative algebra operand, AS. This just means that there's a multiplication. I use red for multiplication from A times A to A. If we consider associative algebra, then in our mind we have an associative law. So this M satisfies some conditions. So I call this relation. I use blue for relations for a moment. So any associative algebra is a vector space with multiplication and this multiplication and satisfy some associativity. Okay, that's associative algebra. A Lie algebra. Again, we have a multiplication, but in most cases, we're not going to use n. We use the square bracket for the algebra, and that satisfy two conditions. One is this skew symmetric condition, and there's a Jacobi condition. So there's a one multiplication satisfying two relations. So this is also an operand. We call it the operand. Okay. So now, what is operand? If we go back to our associative world, given algebra A, associative algebra A, then the representations of A are called modules, A module. Right? Then, if we consider all the associative algebra as a representation of something, that something is an operand. So starting from AS, this operand, all the AS representations are just the associative algebra. Starting from Lie operand, all the Lie representation is just Lie operand. So that's the way to define operand. So let me give you two more examples here. Oh, I should point.
Oh, you have to click on the slide on because we speak AI.
Oh, yeah, okay. Yeah, I don't know which point should I mean.
Yes,
This computer, yes. Commutative algebra. Then, well, we can consider commutative algebra as associative algebra. That's true. But there's a commutative operand which consists of a multiplication satisfying actually two conditions. This associativity is the second one, but also another commutativity, right? One multiplication with two relations. So all the commutative algebra sets have this property. And the Poisson algebra, slightly different. We have multiplication, and then we have a bracket, so that AM is a commutative algebra, and A with a bracket is a Lie algebra. So already we have two multiplications satisfying two conditions, one condition, two to four conditions, and we have one more, Leibniz rule. So we have two multiplications as five relations. So this is so-called the Poisson algebra. Right. So all these examples I haven't mentioned the unit, but we could ask for unitary algebras by adding a unit. But I didn't do that, but it is possible to do that. Okay. Right. So now let me give you an informal definition of operand. Operand, okay. Oh, wait. I don't know which one. Okay. So one way to consider operand, if you don't want to work with operand, you can consider operand is consisting a set of multiplications and a set of relations. I use red for multiplication, blue for relation. So we already have seen some examples, right? So each operand kind of consisting of a bunch of multiplication, maybe more than 5, 10 possible, and also a set of relations could be 100 relations. And the example I gave us 4 different operands. There's a lot more. And all the multiplication in the previous example is from A tensor 2 to A. But in general, the multiplication can be from A tensors n to A for any number n. Okay, so this is a generalized multiplication. Even n equals 0 is possible. if n equals 0, just this is k to a. This is kind of the unit part. Then here's the condition. The connected. Remember at the beginning of the theorem, I moved the connected condition outside of theorem. Okay? That's the condition we're going to give. A connected operand means that there's no one multiplication except for the identity. Right? So like a differential, we don't want to have a differential. Differential, in the greatest sense, differential would not be C times identity. So we don't want to have differential in as our multiplication. This is the only condition in the theorem. Now, the theorem applies to all connected O-algebras. Well, in fact, it's more general. You can do this G equivalent O-algebras or O-algebras of half action, two action, all these. The only thing to remember is that it should be always be connected. Okay. If you remove that one, the theorem will fail. Well, maybe there's another theorem. I don't know. Possibly.
How is the half going to work? To have an antipole?
No. So the algebra A. So suppose you have half algebra H. Then you consider all the O algebra with H action. So this is a kind of category of algebras. Then the theorem applied to that category.
But he's asking, how do you realize half algebras as algebras over the operand, but then you need the props on this.
So that's not, okay, you're not looking at half algebra. That's
No. And not A is not half algebra, but with half action.
Yeah.
Like a group action, right? So G is a group, G you can act.
This concerns operands, not props.
Right, yes.
Mhm.
Yeah. Right. Yes, so that reminds me, so this fails for coalgebra.
Mhm.
The result fails for coalgebra. Yes, thank you. Thank you for mentioning this. All right. Another informal definition is that operand O is like associative algebra. It's kind of associative, it's graded, and as a vector space, you can decompose. Then each ON is considered as a set of operations or n multiplications. Okay, A. I use A to kind of indicate that where this multiplication X are. And satisfy a set of relations. This is a kind of informal definition. And if we really want to work with the category of operand, then any operand is a free operand generated by multiplications, not other relations. It's like associative algebra. We have generators and model relations. It's kind of very, very close. All right. Then probably we can skip this. It's a formal definition. If you know the definition of operand, then you know this. If you don't know, it's not. It's kind of very tedious thing, right? So that's why I put this very small. We can skip. If you cannot read, you can skip because it's very small. Yeah. Okay. So this finish. Okay. Yeah, I guess I already said this. This theorem applies to kind of more broad context need. Actually, what we need is the following two conditions. One is that it is kind of connected in some way. The second one is that we need, if A, B are algebras, then A plus B is still algebra. That condition, we need that condition in our proof. So if A or B fails, then only the part of theorem will. Okay, so okay, so let me go back to, at the beginning. Where is that? Okay, so I explained the meaning of simple. Oh, sorry, my fault. Okay, I should not.
What happens if you go close to it?
Yeah, I think I mean, they don't like this divide doesn't like me.
I think you can continue and if that's maybe, I think, one second. Okay, like, I think if it pops up, it's gonna be after your talk anyway, so like, I think you can continue.
Yeah, so I explained the simple and I explained the operand. I hope we have a good understanding of O-algebra. The next item is simplicial. What is the meaning of simplicial? Okay. Oh, too fast, sorry. Yeah, okay, so the word simplicial only appear once in the theorem, but probably this is one of the most important words in the result. So this theorem is about simplicial algebras. So what is the meaning of simplicial? A simplicial set can be considered as a collection of sets x n. I use x for simplicial set with n beginning with 0. Together equipped with degeneracy maps and phase maps. This is the concept is from topology, satisfying the simplicial identity. So I list all the simplicial identities here. And now, if we want to know the domain of the maps, then probably sometimes we add n. But usually, if you open kind of the homological algebra book or topology book, they can omit n. So there's a S map, these are phase map, and the D, the S map is the degeneracy map, the D is a phase map. So we have a collection of sets with certain maps between. Then another way of thinking about simplicial set is the following. We start with delta, which we call the simplex category. So the category consists of objects. Objects are just integer, positive, non-negative integers, 0, 1, 2, 3, 4. But we want to put a square bracket. But this square bracket is not in algebra modification, right? Just a square bracket on each n, and consider each n as a set from 0 to n. So these are objects of delta. The morphisms from square bracket n to square bracket n is just, it's called, should be non-decreasing. Sorry, this is a typo. Non-decreasing map. Because this is one set to another set. We use the order from small to large. So we consider all the maps. So these are the morphisms. This is called the simplex category. Then another way of defining the simplicial set is just a factor from the opposite category of this delta to the set category. So now, this is the kind of equivalent definition. Then let me tell you how to get, I should say this, how to get the xn. Because in this definition, the x consisting of xn. But in the second definition, it is a functor. So basically, I should write f to be x. Basically, the fn is f applied to n. Okay, then you have a bunch of sets. Then you can consider the category, the form in this category by using that. This is the opposite category delta to set. So this, by definition, this is a simplicial set. And for this simplicial set, it is a set we can count how many elements. Then by the definition before, we can count. I cannot. We can count that the number of elements in the level n is this combinatorial number. Okay. So this is simplicial set. Then what are the examples of simplicial sets? These are lots of examples, but in the last, I don't know, 20 years or so, a very popular topic is infinity category. So infinity category is a simplicial set. So now you know the half of definition of infinity category. Infinity category is simplicial set, satisfying one another condition, additional condition. Complex is again a special case. All right. So this is a simplicial set. Then a simplicial, oh, too fast, sorry. Simplicial object. In the definition of simplicial set, we start with delta, then we map to set category. Then we can replace this set category by any category C. So simplicial C object is a collection of X and with in the category of C, together with the degenerate map and the face map, satisfying the same simplicial identity. Another way is just as a function. It's because now I use X. I should use X in the previous slide. It's a function from the delta object to C. Okay. Two definitions same, just taking the Xn to be that. Okay. So then we can apply. Here's some examples. If T is a topological space, the singular chain complex of some base field, if we use C dot TK, this is simplicial K vector space. So just taking C to be the vector space category, this is simplicial object in the K vector space category. I haven't defined what is co-simplicial set, but you can imagine that what is co-simplicial set. Just replace delta object by delta as one. All right. Then yeah. So now suppose only part 4 kind of is both 3 to 4 relevant. For part 4, if C is a category of O-algebras, O is operand, we can consider all the O-algebras together. This is a category. By the way, it's really easy to form a category, right? Anything is in the category. So if we take C to be the O-algebra, then we use little sc to be the category of simplicial O-algebras. Okay. So now we can talk about simplicial O-algebra, right? We start from O-algebra the category, and then we have a definition of simplicial object on this category. So hopefully this explains the words simplicial. Okay, now why we care about simplicial algebras? Or more generally simplicial methods, because this was used in derived algebraic geometry and the topology category theory, homotopy algebra, simplicial representation theory, generalized cohomology theory. So it appears very naturally, especially for the simplicial commutative, simplicial commutative algebra appeared quite a lot in derived algebra geometry. So this is a kind of the motivation for us to study simplicial algebras. But then we kind of figure out, oh, it works for all algebras. All right. So let's see. Yeah. So remember now.
Sorry, I missed the definition of simplicial algebra.
So we look at item 4. So we start with O-algebras, category algebras. Then we can look at the simplicial object.
So it's an O-algebra in SK.
So K is a base field. Then we can look at the all O-algebras over K. So this is a category. Then we can ask what is simplicial object in this category. Just a sequence of algebras, different levels with base map and degenerate maps. Yeah, thanks. Right, so now I think this is the last item I need to explain. Okay, do I have time still? I got 15 minutes. I did explain what is simple, what is a simplicial, and what is O-algebra. But in the theorem, I need to explain. I don't want to touch this again. I need to explain the red part, right? These KQ cosine KQ phi, these two objects. The best way to explain these two objects is using the dot-com correspondence. So again, there is a kind of small print, so we don't need to worry about this. And we're not going to use a small print, but this is a kind of the theorem from homological algebra, from topology. This is the equivalence between the category of simplicial C objects and the category of non-negatively graded complexes. So C is any arbitrary category now. So the best, the simplest one is a K vector space. This is arbitrary category. Then we can talk about simplicial K vector spaces. And this is the left-hand side. And the right-hand side is a category of non-negatively graded chain complexes. This is the equivalence of category between the simplicial object category and the chain complex category. It's a very nice correspondence. It's called dot-com correspondence. And for the second half of the page, this is the explanation of how to construct the function n. We're not going to use n, so that's why it's kind of small. But then for the function gamma, we do need a gamma. So let me tell you what is gamma. Too fast, sorry. Is this one? Yeah. So a gamma function is from the chain complex category to the simplicial object category. And it's kind of complicated, but basically that's the formula. Remember the simplicial object is a level, different level, n to 0, 1, 2, and so on. So I'm just telling you that level n is defined by this. Okay, that's the top formula. We also needed the shift function to define the next two things. So shift function of complex is kind of obvious, right? Just move this backwards by 1. That's the shift one. All right. So most of this is from the classical homological algebra.
So how does the right side depend on little phi? So there's the right side. On the right side, what is the little phi? I mean, there is no summation.
So the little phi is all the surjective maps from this set from 0 to n to set 0 from to k.
But why k doesn't depend on little phi?
So k is from 0 to n. We need to take the sum of all possible. Yeah, so this is going to be that you need to add all these k, but it's say, I mean, for all the three phi's, the yk is same.
Same.
Yeah, if you fix k, that's same. Right. Okay, so the shifter, we know what is shifter function. Okay, so now next definition. Oh, I think I don't know. Yeah, this is the right page. So now we consider this K vector space category. Then we consider the chain complexes. I need two special ones. One is the degree 0, the position 0 is K, after that is all 0. The other one is K. The map from K to K should be the identity. Sorry about that. I didn't put the identity, but the second one should be the identity. So I kind of just omit all zeros from position 2. Okay. So these are two easy complexes. Then for each Q, I first shift this complex to the position Q. Then you take a gamma. Okay, that's the definition. We start from the easy one, then we shift to the position Q, then we take the gamma. So these are the two simplicial K-vector spaces. Okay, so let's see. Maybe I should have skipped the Hilbert series because I only had 10 minutes for
You started late.
That's fine. Okay, so Hilbert series. Yeah. Yeah, I think we only care about the second item. Because if we skip a Hilbert series, then we don't need to worry about that. The second item says that if we take Q to be 0, so let's go back. Here we have a Q. I don't want to touch, but KQ phi and the KQ psi. So Q is an integer bigger than 0. But if we look, just take a Q to be 0, look at the item 2. These two simplicial vector spaces admit a unique unital associative S algebra structure. So S algebra is for simplicial algebra. I don't want to write simplicial everywhere. So I put little s attached to algebra to this is S algebra is a simplicial algebra. Great. So right, okay, so let's go back. So at this point, I explained all the terms. Do you agree? Maybe you already forgot the theorem at the beginning. But I think I explained all the terms. Right? Yeah. Wait, say too fast. Yeah. Okay. So let me explain to you the algebra structure on these two special simplicial vector spaces. The first one, as I said, we don't need to worry about Hilbert series. Just telling you that if K0 phi, this means that each level is just K. But K, we know what is algebra structure on K. This is just a trivial algebra structure on K. All the face map and the adjacent map is just identity. Then Lemma says there is a unique algebra structure on this vector space, which is simple. And I'm going to skip the algebra structure on the high Q because it's getting too complicated. But this one I can explain. So the next one is a K0 psi. K0 psi. Then each level we have a different algebra. Each level we have a different algebra. So this is a precise construction of the S algebra structure. Each level we first we need to say what is a simplicial structure. This is face map and the adjacent map. So I'm giving all the details here. Then the next, define the algebra structure in this very simple way in this displayed equation. Right? Then psi n is identity. Then under this definition, this becomes a simple unital commutative associative S algebra. S algebra is for simple object. So this is a non-trivial one. If we look at the item 2, I color differently. This is purple color. It said that the K0 psi is not a simplicial field. Because we can consider the category of field, we can consider the simplicial objects in that category. But if we go back to commutative algebra, a simple commutative algebra is a field. But this is a simple simplicial commutative algebra, but it's not simplicial field. So somehow this algebra is kind of non-commutative. If it's really, really commutative, there should be a simplicial field. Each level is a commutative, but simplicial object makes us non-free in some sense. Okay, and this algebra structure is unique. Okay. So I think I explained all the terms. So let's take a look at the theorem again. We have a simple simplicial algebra. Then V is let's mark to 1, 2, 3. 1 is the simplicial vector space with 0 multiplication. This is possible if non-unital case. 0 multiplication is possible. Or is K0 phi times A. Tensor means just a level-wise tensor. Each level with tensor A. Tensor A for some simple O-algebra. So A is a simple O-algebra. Then we have a K0 phi. This is a simplicial vector space. Then at each level we just tensor K. This becomes a simplicial O-algebra, and this is simple simplicial O-algebra. In the item 2, A must have a non-zero multiplication. Could be 3 multiplication. That's possible. Some non-zero multiplication. The item 3, we have a KQ beside A. And for Q beginning with 0. Again, A is non-zero, has non-zero multiplication. Then if we require V to be unital, then the only case 1 will not appear because unital case multiplication cannot be 0. Okay, then we have 4 and 5. These are some case of 2. So now remember in the title I said this is a classification of simple simplicial algebra. Is it a classification result? In a weak sense, because it depends on the classification of O-algebra. If we don't know the classification of O-algebra, then we don't know anything, right? So this is a classification result in terms of classification of O-algebra. Right. So for example, if we consider associative algebra. So the last line, sorry. So if we consider associative case, if O is associative operand, if K is algebraic closed, then every locally simple unital associative S algebra will be of the form K0 psi tensor matrix algebra or K0 phi tensor matrix algebra. The last line, just a copy 4 and 5. Okay, well, if the locally finite dimensional truths, then we do we can classify. So all the classification depends on classification of the O-algebra. Similarly, for Lie algebra, because we know finite dimensional, the classification finite dimensional ones, then we can apply that. Or if infinite dimensional ones, certain Cosmology algebra also simple infinite dimension, then also true. In our theorem, we don't require V to be finite. But we can make some similar remark for Jordan algebra. Okay. Now since I do have a couple of minutes, I can tell you the one key step. So we can introduce a concept of subcation, which is short for supported truncation. And this was used in a crucial way. The idea that we can define a sequence of sub simplicial vector spaces. And if V is O-algebra, then we can prove that the SPL is ideal of V. So now, if V is simple, then you can only see one step. Okay? Because ideal will be either 0 or the whole V. So this is a key step. But after that, we need to analyze this SPV. So then eventually we can prove the result. And by the way, the subcaching is actually very useful in the other result we proved. We have some conjuring lemma for this and existence lemma for the simplicial existence of simplicial algebra structure. And so let's take a final look at the theorem. So we kind of provide a uniform approach to the classification problem of simple simplicial algebras for different operands. Okay, we didn't say we need to be only the some conditions, but only connect all connected operand. How theorem works. Now I put back the connected condition. If O is connected operand from a base field, then in the non-unital case, we have 3 classes. In the unital case, we have 2 classes. So, yeah. Thank you. Thank you very much.
Questions?
I have a question. So in O-class, multiplications are from temporal products of some vector space with itself. As there's also the notion of probe. Even with, we could also consider factors where the multiplications are from one vector space to tensor product itself. So like we have an O-class for algebra and maybe one probe for co-algebra. My question is, for these kind of structures, is there also a simplicial definition of simplicial object or something like that?
Are you talking about the simplicial co-algebra?
Yes.
Yeah. For any category, you can define simplicial objects. Right. So the result fails because the subcation works for algebra multiplication. For co-multiplication, this we cannot prove that the co-ideal. So yeah. You have a question.
You tell us what is the simple simplicial algebra. Does it make sense maybe to define like a so-called semi-simple simplicial algebra and for your classification with your
All right, this is a very good question. So it makes sense to ask a classification for semi-simple simplicial algebras. The problem for us is we don't know how to deal with the extensions. I don't think it will be just direct sum of these. And slightly different. I don't know what is the right definition. We could define a semi-simple simplicial algebra as direct sum of these. But we can also define like intersection of like maximum ideal is 0 something. But if we use a second definition, I don't see how to put these together.
So there is no Artin Wedderburn for this one.
Yeah. Basically, yeah. We can ask if the Artin Wedderburn theorem. Right. Yes.
It's a little bit mature, but so there's the idea of field with one element. And let's open it to this F1.
Say again.
There's this idea of fields with one element, F1. Is it possible to extend this?
It should be, but all our proof is based on elements in some way. So if you can a way to handle these objects using elements. I don't know if that answers your question or yeah. So our approach is kind of using the elements because the subcation definition, I didn't give definition, but kind of element-based definition.
Additional questions? How about the super world? If you look at all algebras in the category of super vector spaces, do you have more choices for the C and the C?
I think in the super world, do we need to do this? Probably still okay, because,
We don't have more choices? I would assume that you have more
yeah,
bases because your C and
possibly
C
the more, yeah,
depends
yeah.
substantially on your.
Right. Right, so, yeah, okay, you're right. So one part of the proof based on the understanding of the simplicial vector spaces.
Mhm.
Then in the super world, there's more to do.
Mhm.
Yes, you're right.
Mhm.
So maybe easy answer is we don't know. How to do this, we don't know how to do this. Thank you, yes. Yeah.
Additional questions? Let's thank James for the great lecture.